Hello and welcome to a new problem solving session. And you can see a problem at your screen, and something about hydrostatic pressure force is being asked. And the problem says that a thin-walled hemispherical cell. There are lots of spelling mistake, but hemispherical cell with a radius r and mass m is pressed against a vertical wall and filled with a liquid of density rho. Through the small opening at the top, you can see this here. Find the magnitude and direction of the minimum force on the spherical cell to keep the liquid from spilling out. You have to make all the things in equilibrium, and friction is negligible, so no friction. Friction is not going to help you anyway. So the purpose of the external agent in order to applying a force must be to balance two forces. The weight of the hemispherical cell, that will be in vertically downward direction, and the force resulting from the hydrostatic pressure of the liquid, you can say. So there will be both components of forces, horizontal and vertical. So we are going to consider first the vertical components of the forces, and you can easily recognize that vertically two forces are acting. The weight of the hemispherical cell, I would like to call it something mg, and weight of the hemispherical cell and weight of the liquid. I guess weight of the liquid, you would like to write it density into volume into g, and density of this liquid is rho, and its volume can be given by 2 by 3 pi r cube, and a g, multiply with a g, and you will get the weight of the liquid. And so vertical component of the force is force in vertical direction, call it x and y axis. So y axis, or call y axis, take the y axis in vertically downward direction. So you can write simply here Fy equal to mg, the weight of the hemispherical cell plus the weight of the liquid, and that is 2 by 3 pi r cube rho g. 2 by 3 pi r cube rho g. That's fine. And in horizontal direction, you just imagine a condition. You must be knowing that in horizontal direction also the fluid is at rest. That means the fluid exerts the same force on the spherical cell as it does on the wall, since the net force on the fluid is zero. So it will exert the same force on the horizontal, on the hemispherical cell and on the wall. So the latter, that the force exerted by the fluid on the wall, can be calculated easily as the product of average hydrostatic pressure force, or as the product of average hydrostatic pressure and the area of the circle that was area of the circle covered by the hemispherical cell, and this will give you the horizontal component of the force, and it will be something on the fluid, on the liquid, it will be in rightward direction. So I would like to write its value simply as here you can see that the average hydrostatic pressure is 0 here, and rho g2 are here. Here the pressure is rho G2R, and here we have a pressure equal to G, so it's average. Simply the arithmetic mean will be 0 plus rho G2R by 2. You can write it 0 plus rho G2R by 2, and this is simply rho Gr. This is the average hydrostatic pressure is simply rho Gr. So the horizontal component of the force V exert, or the wall exert on the fluid, or fluid exert on the hemispherical cell, can be simply written as rho Gr multiplied by pi r square, that is r cube pi rho G. And so the force to be exerted, finally the net force exerted by the external agent, you can write it fx square plus fy square, and you will get, if you calculate all those things, you will get something like G under root rho square r raised to 6 pi square plus 2 by 3 pi rho r cube plus m squared, everything under a square root, and of course its magnitude is this, and the direction, if this force makes an angle theta with the horizontal, then you can simply write tan theta equal to fy upon fx. And this is a simple problem. Thank you very much for watching.